So hello guys, this video would be more informative and interesting as well. So in previous lectures we have seen about the psychometric processes, and now today we are going to see our next process, which is adiabatic mixing of two streams, and then we will solve a numerical based on this psychometric chart. So now moving towards the content. So what is exactly adiabatic mixing of two streams? We will see first, and then we will solve a numerical. So now, a psychometric process that involves no net heat loss or gain during the mixing of two streams is called adiabatic mixing of two streams. In the chart here, we can see point number 1 and point number 2. So point number 1 is a first stream, point number 2 it is second stream. Means two different temperature streams are mixing together with the constant enthalpy. So we will get one point or temperature which is mixing of stream point temperature, where which will be exactly in between these two lines. We can solve this like, if we are having fraction, means if we are having two streams, one air is passing with a fraction of 40%, and from the second pipe it is passing 60%, and then these two streams are mixing. And let's suppose our first pipe air is having temperature of 20 degrees Celsius, and second pipe is having 60 degrees Celsius. Now this two air would be mixed at point number 3, let's suppose, and then we have to find the what will be temperature at point number 3. Means if two streams are mixing there, and we have to find the state of that point or state of that air mixing air. So from this formula, or from these steps, we can, from this concept, we can easily find out the temperature of point number 3 or mixing point. So here is one schematic diagram as we discussed. From point number 1, from point number 2, two airs are coming. Point number 1, air is having mass of m1, enthalpy h1, and humidity of w1. Similarly, M2 H2 W2 is mixing at point number 3, which is having different mass, different enthalpy, and different specific humidity. So now, when two quantities of air having different enthalpies and different specific humidities are mixed, the final condition of air depends upon the masses involved and enthalpy and specific humidity of each of the constituent masses which enter the mixture. So now, what is the meaning of this? So let's suppose point number 1 and point number 2 airs are mixing. So we get point number 3 of mixing air. That temperature would be ranges between 20 to 60, because we have taken some. Let's suppose we have taken one example. From stream 1 temperature is for 20 degrees Celsius, and of stream 2 temperature is 60 degrees Celsius. So we can say that the temperature will be range between 20 to 60, depend upon its fraction. Let's suppose 40% is from stream 1 and 60%, remaining 60% is from stream 2. So more temperature would be inclined towards the higher weightage or higher mass of stream, which is 60 degrees Celsius. So temperature would be near around 45 to 50 degrees Celsius. So that is basic idea behind this. So now we have to derive one formula. So now M1 is a mass of air entering at point number 1. H1 is the enthalpy of air entering at point number 1. Wn is specific humidity. Similarly for point number 2 and point number 3. Now mass would be same, because M1 and M2, M1 plus M2 is equals to M3. Well, their mixing is taking place. Now by the energy balance, M1H1 plus M2H2 is equals to M3H3. And now mass balance of the water vapor is M1W1 plus M2W2 is equals to M3W3. Substituting the values of M3 from equation 1 and 2, we will get as M1 divided by M2 is equals to H3 minus H2 divided by H1 minus H3. Equation 4 we can write. Similarly, from the equation 3, we get M1 by M2 is equals to W3 minus W2 upon W1 minus W3. These are depending on the if we are having enthalpies, so we can get and mass flow, so we can easily get the ratio. And if we are having the specific enthalpies W, so we will get in this form. And now generally we can write M1 divided by M2. Here M1 and M2 are the masses of two streams, which will be given in a numerical, or they can simply give the fraction. So M1 divided by M2 is equals to H3 minus H2 divided by H1 minus H3 is similar to W3 minus W2 upon W1 minus W3. So here one picture is shown, which is it is fog. So when the fog is occurred, so it's actually saturated air. When the temperature of when the enthalpy and temperature is reduces beyond the saturation line, so this process occurs. So in the psychrometric chart, we can show the fog region. Here hatch line region is fog region, and when the line passes beyond the saturation curve, that region become fog. So that is about this. Now here simply shown all the processes in the chart. Now moving towards the example. So question is this question is taken from the RS Kurmi book. You can refer that book also. So here we will see a numerical. Air flowing at the rate of 100 meter cube per minute at 40 degrees Celsius variable temperature and 50% relative humidity is mixed with the another stream flowing at the rate of 20 meter cube per minute at 26 degrees Celsius variable temperature and 50% relative humidity. Here two streams are given. One is having mass flow rate of 100 meter cube per minute and having temperature of 40 degrees Celsius and relative humidity of 50%, and second stream is having mass flow rate of 20 meter cube per minute and temperature of 26 degrees Celsius. Now these two streams are mixing. Here both relative humidities are same. Now the mixture flows over a cooling coil whose apparatus dew point temperature is 10 degrees Celsius and bypass factor is 0.2. So we have to find dry bulb temperature of and relative humidity of air leaving the coil. If this air is supplied to an air conditioning room when dry bulb temperature is 20 degrees 26 degrees Celsius and relative humidity of 50% are maintained. So we have to find room sensible heat factor and the cooling load capacity of a coil in terms of refrigeration. So here given are volume flow rate of both streams. V1 is 100 meter cube per minute and temperature is 40 degrees Celsius and relative humidity is 50%. And volume flow rate of second stream is 20 meter cube per minute and TD2 is 26 degrees Celsius. In schematic we can see both the streams are mixing and then mixture is passing through the cooling coil which is having bypass factor of 0.2, and now this mixture is passed to the room which is having the temperature is 26 Celsius. Now moving towards the next, from the psychometric chart we have to draw these points, point number 1, point number 2 mixture points, and then from the psychometric chart we are having the enthalpy H1 is 99.8 kilojoule per kg of dry air and enthalpy of point number 2 is H2 is 53.5 kilojoule per kg of dry air. Now we have to find the mass flow rate. M1 and M2 we have to find initially. So M1 is basically V1 divided by specific volume. V1 is volume flow rate. So now we have to find the volume flow rate or specific volume at the point number 1. Vs1. Here point number 1 is there. If we find in the chart we can get point number specific volume at point number 1 which is 0.92 meter cube per kg of dry air. Now similarly from point number 2 we get as 0.862 meter cube per kg of dry air. Now at point number 1 we get mass V1 upon Vs1 V1 we are having 100 meter cube, and now Vs1 is 0.92. So we get mass at point number 1 is 108.7 kg per minute. And for similarly, at point number 2 we get mass flow rate as 23.2 kg per minute. This combined mass we get Ma3, which is 131.9 kg per minute. M1 plus M2 we get M3. In the chart here, right, we can see first point, our second point. First point is having a initial condition of a first stream, and second point is a second stream. And now we will get third point in between 1 and 2, because it is a mixture, and we are having more mass at point number 1. So uh, so the point number 3 would be more inclined towards the point number 1. Now for the energy balance equation, m1 h1 plus m2 h2 is equals to m3 h3. By this formula we get h3. H3 is the enthalpy at point number 3. So h3 is ma1 plus h1 ma1 h1 plus ma2 h3 h2 upon ma3. We are having these all values, so we will get h3. From the chart, we from the chart at enthalpy line we get h3, and joining to this line from point number 1 to 2 we get point number 3. So drawing the straight line at dry bulb temperature we get point number 3. So we will get all condition at point number 3. And if we are having dew point temperature, apparatus dew point temperature, we have to join point number 3 and ADP. So it is what we are having, room sensible heat factor line. We have seen in our first lecture of this chapter, room sensible heat factor line from point number 3 to ADP. And due to bypass factor, the point number 4, which is last point of our process, which is a temperature of air inside the room, which is coming in between ADP and point number 3, and the remaining part at point number 4 and 5, it is bypass factor. So now solving, we have got point number 3. So now the dry bulb temperature and relative humidity of air leaving the coil, we have to calculate the with the help of bypass factor. We have to find TD4, which is temperature of air leaving the coil. With the help of bypass factor, we get TD4 minus ADP upon TD3 minus ADP. We have apparatus dew point temperature or coil temperature we have given as 10 degrees Celsius, and uh, we are having TD3, so we will get TD4 here as 15.52 degrees Celsius. From the psychrometric chart, we find the relative humidity of air leaving the coil at point number 4, which is 92%. So now we are having all these points, point number 3, point number 4, point number 5. These all points we are having now. So we will solve room sensible heat factor. First question was we have to find room sensible heat factor. Now from the psychrometric chart, we find the enthalpy at point number 4, which is 42 kilojoule per kg of dry air. Now here in this diagram we can see our basic process from point number 2 to 4. So we have one point here, 1A, to get the enthalpies at latent heat and sensible heat for the process. Now, what is room sensible heat factor here? Room sensible heat factor is the difference between enthalpy, ratio of sensible heat upon total heat. So sensible heat we can get HA minus H4, and total heat get are from H2 minus H4. So dividing it we get room sensible heat factor of 0.913. And our second question was cooling load capacity of a coil. So cooling load is total heat removed from the air multiplied by mass of air. So here enthalpy difference between point number 3 to 4, H3 minus H4 multiplied by mass of air, total air. So that comes 65658.8 kilojoule per minute. This is in kilojoule per minute. To convert it into ton of refrigeration, we have to divide by 210. So we get 31.185 ton of refrigeration. So that is our numerical based on the psychometric chart. That's all for the today.